So, to get to the margin of error, I'm going to start with the standard error. And this is the only time in class we'll do this intermediate step. Because I like going straight to the margin of error in general, and you guys don't care enough about the math, and that's totally fine. I'm not saying you should. But I want to build it today to show you what the actual TI is going to be vomiting out when it gives you its results. Standard error, we have to take that S and divide by the root of N. So we're going to have that 0.025 pounds divided by the root of 30. Let's get a value for that. It's going to shrink it considerably, yeah? I get 0.005. I get 0.005. Now you might be wondering what the hell that is. Good. I mean, it is the standard error. But you might be wondering where that is. Describe to me what just this is. Describe to me what just this value is here. Just S. Think 243. Forget 244 for a second. What does S mean? The sample standard deviation. In your own words. What is it a measure of?
The averages of the highs and lows.
Say that again.
The averages of the highs and lows.
Brian, I love this. It's an average of highs and lows, and actually everything in between, isn't it?
Right.
Isn't it keeping track of all the distances of all the data points from the average to them, and it kind of averages them all together? I taught my 243s. You guys remember how I taught you had to use the word average twice? Do you remember vaguely this? It's the average distance of the data points to the average. That's kind of the rough, you've all forgotten. It's totally fine. It's totally fine. It's been a long time. But exactly, it's basically a measure of variability. So you're trying to describe the spread in your data. So pictorially, when you envision your sample data, and we did do this, yes, we actually drew a histogram if I remember correctly, and it looked kind of bell-shaped. It was kind of like this, and it could have been a little bit skewed. But this thing had a center, x bar, and then that center has a spread. So this is x bar minus x up to x bar plus s. If you go out a little bit further, this is x bar minus 2s up to x bar plus 2s. Fair? Okay, that's what S is. S governs your sample data, and also its distribution. And it tells you something. It tells you something. If the data is bell-shaped, you've got certain percentages within certain ranges, right? If the data is not bell-shaped, you don't get those percentages, but S is still measuring the distances. So this distribution, it might not look like that. It might look ridiculous. It could be U-shaped, it could be X-shaped, it may be any shape, really. I mean, it could look like this for that matter. It doesn't matter what it looks like. You're never going to know what the population is going to look like, so the sample could be anything, really. So, how does that tie to this? What happens when you divide by root n? Mathematically, it gets smaller. That makes sense. But where does that live? Like, visually, where does that live? This is the hardest question I've ever asked you in 3 weeks. Rory, go!
What's root n again? Sorry.
Well, n's a sample size,
Okay.
and root n is the square root of that sample size,
Okay.
which might seem magical, but that's just a consequence of the central limit theorem.
All right.
The hardest question, Elizabeth?
Variables?
Yes, you know what? Yes, absolutely. Now, how much confidence? This is a tricky question. This is also very tricky, very nice.
95.
No, not quite yet. Not quite yet. When you don't multiply by anything, I think somebody just whispered it. I'll help you. I'll help you. So, where it lives in this interval is you take your sample data. If you don't stop there, you go to what's called the sampling distribution. Now, the sampling distribution is something you have completely forgotten from 243, and that's okay. But what it is it's the distribution of all possible averages that you could have gotten if you ran this experiment. We got one, 0.05, or whatever the hell it was, 0.526. But this number line represents all possible averages we could have gotten if I went to Del Taco and bought 30 burritos.
So that's like all those little green diamonds that you have?
Say that again.
Like all the green diamonds on the on that thing yesterday?
Yes. Remember the last in classics exercise we did in 243 with the funny dice? And I made you guys all roll in different groups and then put all your results together into one big histogram? You've probably forgotten this too, it's okay. But what happened then You put all of those green and orange and blue and yellow and whatever other colors we're talking about together, and the distribution came up looking like this. No matter what the original distribution looked like, they all came out almost perfectly bell-shaped. Again, because of the sampling size governs, thank you, Brandon, the sampling size governs how tight the curve is. It might be super tight and tall, it might be super wide and low. Because of the central limit theorem again, he guaranteed a bell curve. The tightness is governed by the sample size. So in this particular, I shouldn't have done that, but that's okay. I love the fact that you brought that up. So this curve by the central limit theorem is guaranteed to sit right at x bar. Within, Elizabeth, a margin, right? So this is how you start building that margin. Because you're never going to hit it perfectly, right? All those diamonds, like Chris said, all those diamonds, it's exactly the connection I wanted you to make. So what you do is you give it the wings, the margin. The beginning of the margin is one standard, what's called standard error. So if you go down and up, x bar minus s over root n, x bar plus s over root n, what percent of the averages have you caught? From memory. From memory. You've caught about 68%, assuming this is a perfect bell curve. Assuming this is a perfect bell curve. That's the connection. So why don't we stop there? It's not confident enough. We want more confidence. And that, my friends, was the whole point of the Guinness talk yesterday.
We're Americans, we always want more.
Well, can I say it a different way? I want to be wrong less, if that's okay. I want to be wrong fewer times than I'm correct. So right now, I'm only going to be right two out of 3 times on average, because 68% is about 2 out of 3. That's why we need this multiplier. This guy right here tells us what to multiply by to bump it out how many. Now, you might have forgotten this from Tuesday, though. The t curve is not quite exactly the same as the z curve. Let me see if I can explain why. Well, we did with the Excel spreadsheet, but what I want to do is I want to show you how we used to do this before we had technology. Hopefully this link works. Yes. Come on now. This is called a t-table, a t-distribution table, if it opens correctly. Fingers crossed, that's the right link. Yes! All right. Now, if you had me for 243, you've never used this chart before. Uh-oh, it just froze. There it goes. If you had Donna, you may have used this chart. Does this look familiar to you guys that had Donna? No, you didn't. Okay, so she's even gotten away from it. Good. Good for her. Good for her. Sometimes she refers back to it, sometimes she doesn't. That's good. So here are what are called t-distribution critical values. Now, the chart is definitely interesting to look at. It's definitely interesting to look at. So what it's asking you to do is, all these numbers here, those are t values. Those are those multipliers that you put out in front of your standard error. Notice how big some of them get. 63, 31, those are huge numbers. Remember what the z-score is for 95% confidence? 2. 2. Holy crap, 63. But you got to remember, that means 1 degree of freedom, and this is a weird term, that means a sample size of 2. If you were only able to draw a sample size of 2, which would have 1 degree of freedom, you better accept a hell of a lot of error in your estimate, right? Does that make sense? I mean, we have to. We have to accept that much error in your estimate. As your sample size goes up, these are beginning to shrink, because remember what happened yesterday on the Excel sheet when I was increasing the sample size? What happened to that t-curve? It came up almost exactly to the z-curve. Thank you, Ben. Nice. Nice. So our job is to figure out which one of these numbers should we use. So the first thing you have to do is you have to make, I think we're okay with this. We would have, how many degrees of freedom would we have with 30 burritos? We'd have 29. Remember the n-1 in the sample standard deviation calculation? It's that again. That's why it's n-. You're going to see a lot of n-1s in this class too as we go through. We'll deal with them all in turn. So we need to be in this column, or this row right here. So now the question is, which one do we use? 2.756, 2.462, 2.45, 1.699, 1.3. I don't know. Which one should we use? Want to roll a die and pick it? Let's not. Let's pick. We're going to go for the middle one. Why the middle one? Because it's in the middle.
It's 3.
Because it's 3.
Up at the top. Isn't that?
Oh, you look at the top? Good. Elizabeth is going, wait a minute, there are some column names. Why do we have 5 columns? Let's go ahead and look. So if you go up here, you can ignore, for now, please ignore this area in one tail because that doesn't make any sense for us yet. It will make sense soon. area into tails. Now this is a little bit cryptic because it's a little bit old school. But what they're telling you to do is draw a symmetric curve